So in class, we were reviewing for my geometry honors final, and obviously I wasn't paying attention because I haven't learned a single new thing in this class. So instead, I took like a problem that's kind of like this, and I overcomplicated it like the entire class period. And I thought this one was really fun because it was a cool integral that I used. I've always wanted to have an integral that like utilizes the fundamental theorem of calculus, and so I combined that with a limit, and you'll see why there's a cool trick there. Anyway, given that theta is equal to the inverse sine of the limit as x goes to infinity of x to the power of -2 times the integral from 67 to x of 2 alpha squared divided by alpha plus cosine alpha d alpha, and that's in degrees, find the volume obtained from revolving this. So this is a triangle thing. You'll see in a second. Okay, so obviously, first thing we gotta do, start with this right here. But the sine -1, there's no trick you can do with that. You're just going to have to apply that to whatever's inside here. And the biggest chunk that we can take out of it, we want to split this into the smallest chunk possible. The smallest thing we can take out of this is the limit to this degree sign right here. So what we're going to do, we're going to bring that over here. We're going to bring the limit. Okay, so looking at this, it's hard because integrating this is not great. But then applying the limit to this, we still have all this alpha stuff left over. And there's no way we can evaluate the inverse sine with a bunch of alpha stuff left in there. So there has to be a clever way to get rid of alpha. And indeed there is. Because if you notice this x to the -2 right here, that is the same thing as 1 divided by x squared. So everything in here is just a quotient. So we can rewrite this as the limit. I know it's a little cramped tightly in there. Hopefully you know what I'm talking about. I'll make it bigger for the next thing. But you'll notice we have a limit as x goes to infinity and a quotient. So we want to use L'H Rule because then we can apply the fundamental theorem of calculus. That's what you should be seeing here. Because as you can see, we have a constant to x. So if we could just differentiate that, then essentially all the alphas go away and we have everything in terms of x, and x approaches infinity. But in order to do that, we have to actually verify that this is going to be equal to 0 over 0 or infinity over infinity. So we know that x squared right here, as x goes to infinity, that's going to tend to infinity. This right here is a little trickier, but, not really. Down here, cosine of alpha is just going to oscillate around. We kind of can ignore that here. Alpha, okay, so that's going to go to infinity. But we have a dominant term up here, which is 2 times alpha squared. That's going to dominate. So effectively, we get a function growing to infinity, and the amount of area under this curve is also going to infinity. So we have an increasing function, more area as you go, because it's going to infinity, over essentially area under here that's going on to infinity. So this also approaches infinity. So we do actually get the result infinity over infinity. And so now we can apply L'H Rule, and we can differentiate the numerator and the denominator. So we get the limit as x tends towards infinity. So we're differentiating the top and the bottom. This right here, derivative of x squared, everyone knows it's 2x. And then here we have the derivative of this integral from a constant to x. And so if you know the fundamental theorem of calculus, this just gets reduced to this inside right here, but all the alphas have x plugged in. Now, if you want to see a proof to that, I'll link it in the description. But it just basically comes from the fact that derivatives and integrals are inverse operations. Okay, apologies, I had to use the restroom real quick. Anyway, what we can do next is you can immediately see we have some really cancelable stuff. We could cancel the 2x and the 2x, and we get this new limit, which I'll bring over here, as x tends towards infinity of, what do we get? Oh yeah, x over x plus the absolute value of cosine x. Now, we can multiply the top and bottom by 1 over x in order to take this limit. So what this will do is we get this right here at the top will cancel, so we effectively get... So now we get the limit as x tends to infinity of 1 divided by 1 plus absolute value cosine x divided by x. Now, This right here, since it's absolute value, the normal range would be from -1 to 1, but here it's just going to be from 0 to 1. So this is going to oscillate around from 0 to 1, and this thing is going to grow indefinitely, which effectively gets this term to 0. And we have a constant here, so our limit is actually just going to be equal to 1 over 1, or 1. And we'll notice that our original statement says we're taking the inverse sine of this limit right here, this right here. So what we can do is we can get that theta is actually equal to the inverse sine of 1. Now, keep in mind this is in degrees because it's stated up there. I know that looks like a power of 0, so if you were hoping you could just get that all to 1, no. It's kind of poor notation, but I didn't know how else to do it. I could write like DEG, but I didn't. Anyway, everyone knows this is 90 degrees because if you think about it, the sine of 90 is 1, so you take the inverse, you get 90. So now we know that theta is equal to 90 degrees. So let's go ahead and box this because it's an important result. So now we can kind of just draw a little barrier here. Now we have this diagram from the very beginning. With a 6, a 20, and our axis of revolution. But the interesting thing is because this is theta, now I purposely didn't draw it as a right angle in the diagram so that you don't just skip to the end and you actually think you have to find theta. Because, I mean, if you did have to find theta, you actually wouldn't need calculus. You can just find this triangle down here as well, then subtract that cone's area from that big cone's area. But I actually was nice, and now that you found the value of theta to be 90, this diagram, it's a diagram of a right triangle, so I can just change this diagram to be a little more intuitive now that we know this is a right angle. And this is 6, this is 20. So now when this is revolved around the axis, we're going to get a cone. And this cone, now it might be tricky to visualize, but this cone is going to have a radius of 20 because as this triangle right here rotates around, it effectively adds another 20 right here, which will be our diameter, but the radius is still going to be 20. And then the height here, which is that portion right there, is going to remain 6. So this cone would be more like that, but just for the sake of drawing a cone, it's not a big deal. But we know the formula for a cone, for a cone's volume, is equal to 1/3 the area of the base, so pi r squared in this case, times the height. And in our case, that's going to be equal to 1/3 pi times 20 squared times 6. Now we can go ahead and cancel the 1/3 and the 6. 6 divided by 3 is just 2. And now we get 20 squared, which is 400. 400 times 2 is 800, so we get 800 pi. So our volume is going to be equal to 800 pi. And that is our final answer.